A square loop of wire, 10 centimeters on each side, moves from left to right at a constant velocity, passing through a 6 Tesla magnetic field directed into the page. It takes 0.1 seconds for the coil to enter the field, 0.5 seconds to travel through the field to the other side, and 0.1 seconds to fully exit the field. And the total resistance of the wire loop is 20 ohms. In Part A, determine the magnitude and direction of the current induced in the wire loop while it is entering the magnetic field. So Faraday's law is the EMF is equal to the change in flux over time, and in this case there's no flux initially because it's completely outside the magnetic field, so we can write down the change in flux as the flux final minus the flux initial. And we just said the flux initial is 0, and that's divided by the time. So this is equal to the final flux, which is BA. We can leave off the cosine of theta since the loop is perpendicular to the field. So BA over T is equal to 6 for the magnetic field times the area of the loop. It's 10 centimeters on each side, so that's just a square, 0.1 squared, divided by the time of 0.1 to enter the field is equal to 0.6 volts. And the current from Ohm's law, the EMF divided by the resistance, 0.6 divided by the resistance of 20 is equal to 0.03 amps. And as far as the direction goes, since the magnetic field, magnetic flux is increasing because it's going from 0 up to something into the page, the induced magnetic field is in the opposite direction, which is going to be out of the page. So using your first right-hand rule, punch your fingers out of the page, and you'll see that the induced current, the direction of your thumb, is counterclockwise. Part B. Determine the magnitude and direction of the current induced in the wire loop while it is passing through the magnetic field. Well, the main thing to note here is that as it's passing through the magnetic field, nothing is changing. It's in the same magnetic field the whole time, so the change in magnetic flux is just equal to 0, which means the induced EMF is equal to 0, which means the induced current through Ohm's law is also equal to 0. In Part C, determine the magnitude and direction of the current induced in the wire loop while it is exiting the magnetic field. So this is basically the same as Part A. It is the EMF is the change in magnetic flux over time. So if we did the final flux minus the initial flux, this time it is the final magnetic flux that is equal to 0, as it is now out of the magnetic field. So this will just equal to negative BA over T, but since we're only concerned with the magnitude of the EMF, we don't care about the negative sign, so we can just kind of ignore that. So this is exactly equal to what we had in Part A, which is 6 times 0.1 squared divided by, it takes 0.1 seconds to exit the field, and that is equal to 0.6 volts, which means the current is the same as before, 0.6 over 20, which is 0.03 amps. What's different now, though, is that as it's exiting the field, the induced magnetic field is going to be in the same direction because the field's getting weaker. So the induced B is into the page, and using your first right-hand rule, that means that the induced current, with your fingers pointing into the page, the induced current in the direction of the thumb is clockwise. For Part D, how much energy is dissipated in the wire loop as it enters the magnetic field? Well, we first figure out the power, because power is related to energy, And there's three equations we have for electric power, which is I times V, or I squared times R, or V squared over R. And because I know the EMF, and I know the current, and I know the resistance, I can actually use any of these three equations. I'm going to go ahead and use the I squared R, since I was what we solved for in part A. So it's 0.03 squared times the resistance, which was 20, gives you a power of 0.018 watts. And now since power is equal to work over time, or energy over time, we can rearrange that and say that energy is equal to power multiplied by time. So 0.018 watts multiplied by the time it took to enter the field, which was 0.1 seconds, is equal to a total energy dissipated of 0.0018 joules. For part E, use the answer to part D to determine how much force is required to push the wire loop into the magnetic field. Because if you look at this loop entering the field, we said as it enters the field the current was induced counterclockwise. So that means in this loop the current is going around in this direction. So in the first side over here that enters the field, the current is going upward. And if you use the second right-hand rule, you know that a current in a magnetic field has a force acting on it. So using the second right-hand rule, if you put your fingers pointing up toward the top of the page and curl them inward toward the magnetic field, your thumb is pointing to the left, meaning that there's a force pushing this wire to the left. So you actually have to apply some force to get this wire loop to enter the magnetic field, since there's an opposing magnetic force on it. So the work is equal to force times the displacement, and the work is the same as the energy, which we just figured out in part D. So I can rearrange this to say the force is equal to work over distance, that's 0.0018, divided by the distance. The wire is going to travel a distance of 0.1 meters, because that's the length of the side of the wire, so divide by 0.1, and that is equal to 0.018 newtons of force to get the wire into the field. And we can confirm that in part F by using the equation for the force on a current in a magnetic field. F is equal to ILB sine of theta. We don't have to worry about the sine of theta since it's perpendicular to the field, so just I times L times B. The I was solved for as 0.03 amps times the length of one side of the wire, which is 0.1 meters, times the magnetic field that is entering, which is 6 Tesla. And when you multiply those three together, you get the same force you got in part E, which is 0.018 newtons.